We've sent our spacecraft to Mars, and although we tried to clean them off, we have probably included some hardy travelers along with our spacecraft, extremophiles that we know can do well in the most extreme environments. Could they survive and replicate on Mars? We don't know, but let's hope we haven't completely contaminated the surface of Mars yet. We probably haven't. It'd be fine, right? But it sure would be helpful if there were ways that Mars itself could be protecting its surface from Earth life so that we can actually go and explore the planet and not worry about contaminating with our Earth life. And my guest today has some good news. So today I talked to Dr. Corien Bakermans. She's a professor of microbiology at the Altoona campus at Penn State University. And she completed research where they exposed tardigrades to simulated Martian regolith to find out what would happen to the tardigrades. She found that in the Martian regolith, you've got compounds, various chemicals that are leaching out into the water solution, that some of it was having some kind of effect on the tardigrades, slowing them down, giving them a harder time. And when they washed the regolith, those problems went away. So there appears to be chemicals that leach out of the regolith that will inhibit Earth life. And that's good news because, if we do send our spacecraft or even eventually people walking around with our biome inside our gut, with the bacteria on our surface, some of this is going to be extremophiles, some of it's going to find its way into the environment. It'd be nice to know that Mars itself can protect itself from our forward contamination. So it's interesting research. Enjoy this interview with Dr. Corien Bakermans. Corien, I think we're all fascinated by the tardigrade. It is both hardy and adorable. What's it like working with those water bears?
I couldn't agree more. They are absolutely adorable, and it is very fun to watch them trying to walk around and swim around under the microscope and learn more about them.
How far away are they from us? Like, if I walked outside, would they be hanging on droplets on trees? Like, where would I find my own collection of water bears if I wanted?
Yeah, so tardigrades are in the environment all around us. Some of their preferred habitats are in mosses and lichens. They do tend to well, I don't know if I should say but they do well in habitats that do have a periodic drying out. So actually, the moss on the roof of houses is a great place to look for tardigrades.
And if I wanted to collect some, what would I do? Like, grab some moss, put it in a water solution, look under a microscope?
Yep, you would grab some moss, you'd put it in water, make sure it was nice and hydrated to wake up any tardigrades that were dormant at the time. And then it's helpful if you can kind of concentrate them a little bit with some kind of sieve. And then, you can look at them under the microscope.
Oh, that sounds great. Yeah. I would probably do that. I've been meaning to buy a microscope and both to kind of search for micrometeorites and sort of examine the soil life in my garden. But I think that would be great too. Another reason. So then I want to understand the research that you were doing. So you were looking at sort of like, what does Martian regolith do to life? So what was explain the setup?
So as we go to Mars and plan to go to Mars with people, right, we want to know if that regolith, which is the loose minerals on the surface of Mars, could be useful. Could it be damaging? Where does it stand in terms of how we will react to it when we get there? And so we decided to use tardigrades as a model organism because tardigrades are known for their hardiness. And if we are going to Mars and we want to try to grow plants or something, then it would be certainly very useful to have organisms that could be dormant on the ride over and then be woken up for, addition to a soil ecosystem and help plants grow. And also, these tardigrades as small animals can help us just better understand how that regolith might have an impact on our own cells, our own bacteria, everything that we'll be bringing with us to Mars if humans get there someday.
And had versions of this research been done with bacteria, things like that?
Yes. So versions of this have been done with bacteria to try to understand the exact same thing. Is the regolith going to be useful? Is it going to be harmful? Where does it stand?
Yeah. Okay, so that was the question that you had. And so what was the setup? We don't have any regolith from Mars yet. No sample return has brought any of that back home yet. So what did you have to work with?
So, because, yep, as you said, we don't have actual Mars samples, the scientific community has worked to develop simulants that mimic the composition of the minerals on Mars, as we've determined from the rovers and the satellite data that we that have been interrogating different portions of Mars for many, many years now. And so, from all that data, several different groups of researchers have worked to create uh, mimics of those environments.
You can actually buy these. Like I just did some Googling, and you can buy lunar simulant, Martian simulant, and even asteroid simulant if you want, from different kinds of like carbonaceous chondrites and various asteroids. And so if you want to have a little piece of simulated Mars, you can. It's not that expensive.
Yeah, absolutely. And that's what we did. We went to the commercially available Mars simulant because it's commercially available, then in such large amounts, many people can work with it. And that's good for comparison studies as well. So we like that aspect of it. We also worked with a researcher who had developed some alternative simulants, and she generously gave us a small amount to work with as well. So we had two different simulants that we could test the tardigrades against. And interestingly, the two simulants were actually meant to mimic the same location on Mars, but they are just a little bit different in how they were made and their properties. And we did end up seeing a difference in the response of the tardigrades to them.
Right, right. So then the question is like, which one is going to be closer to the real stuff?
Yes.
And so what is in the Mars regolith, and maybe what would make it different from what's in Earth-based regolith?
Yeah. So let's see. I'm looking at my table of chemical composition right now. And one thing that's not in Mars that is on Earth is organic material. So that is a big difference. The lack of organics is very different. And also, the minerals on Mars are very oxidized because they've been subjected to ionizing radiation for many years. And so they are much more oxidized than we have here as well. And a high iron content, which is similar to some soils on Earth, but very typical of Mars is the high iron content.
Right, and that gives us that red color
Yep.
on the regolith. Okay, now one of the big issues, and I'm not sure if this was included in your simulated regolith, is that on Mars it's about 1%, half to 1% perchlorate, which is another sort of result of this radiation coming from the sun. So when you buy the regolith, does it have those perchlorates in it as well?
It does not. There is a little bit of chlorine, but I don't think the perchlorates. This is knowledge I don't really have in my brain. I'm not sure how easy they are to produce and then keep stable here in a simulated Martian regolith.
Right, right.
So,
And like and I think it's important just because like that stuff's poison,
yes.
and life does not appreciate perchlorates. And so the tests that you're doing are essentially without perchlorate, and still you saw a degradation in the life.
Yes.
Yeah.
Exactly.
Okay. Yeah. All right. Okay. So how did you sort of run the experiment?
So we took some tardigrades, and so my collaborator Matteo, he collected the tardigrades from the mountains in Italy, the Apennines, and he collects them in their dormant state, and shipped them to me. So first thing I had to do was wake them up, and you do that by hydrating them. And once they were woken up, then I mixed them in with the different regoliths, and I let them sit with them for not a super long time. This was a short-term experiment, but about a week. and over time just checked on them to see how active they were remaining. And so, right, I'm looking for them to be walking around and doing their thing while they're in there or not.
And so how do you tell an active tardigrade versus a sluggish one?
So they are, when they're active, they are very active. They are swimming around, they're walking around on the particles, and you can quickly identify them as active. When they are feeling the ill effects of something, they will stop moving and yeah. So that's what we're using as a measure. It's not 100% accurate, right? There could be some that are not moving and are still alive, but that is our metric.
Okay, all right. And then, if I recall from the paper, you then tried some various things to improve the condition of the regolith. So what did you do?
So as we saw that, so we used one regolith called MGS1, and it was very harmful to the tardigrades, and they stopped being active very quickly upon exposure to that simulant. So since we know that the tardigrades aren't immersed in water, then anything that is water soluble in that simulant is going to have a bigger impact on them if it is harmful. So we decided to test that basic idea by washing the simulant, washed it 4 times in a row. And that washed simulant, then I could measure that it had fewer solutes than the water that was combined with unwashed simulant. So we could just see on a very big picture level that there were fewer solutes or salts in the water with the washed simulant.
Okay, so this is like me just putting the rice in the rice maker, putting in the water and starting it up versus me washing the rice until it runs clear and then putting it into the rice maker and putting in the water and starting it up.
Yeah,
Okay.
exactly.
Yep. So then what is the stuff that was dissolving into the water?
So we did, so we don't know for sure. We did not measure that, but other researchers have measured it, and it seems that sulfur, calcium, and potassium are the most predominant ions in extracts of this simulant.
Right. And so, like, if I just took like an iron heavy rock or a rock that had a lot of these kinds of chemicals in it, just ground it up, mixed in a little water, would I, just an earth rock, would I probably see a similar result? Sad tardigrades?
It depends a lot on the rock.
Right.
So, I mean, sulfur is known to often be a damaging component. There are many iron sulfide minerals on Earth as well. So yes, if you had high sulfur, that would be a potential problem. But there's also a lot of rocks on Earth that would not pose a problem to the tardigrades.
Right. So it's just like this specific chemical mix that is on Mars is an issue. Okay. So then, I think, and in the sort of the research, and maybe it's just from the press release that was associated with what you were working on, the real impression here is that, okay, it looks like Mars has some kind of natural protection to Earth life, which would be good news for some kind of forward contamination from our exploration of Mars. So how would you kind of hypothesize this would extend to actual Mars with, actual human bacteria coming along for the ride?
Yeah, so this is some good news from that perspective, because if the regolith itself is potentially damaging to organisms, then as we send rovers to Mars, we can rely on that fact to help prevent contamination of Mars from earthly organisms, which, right, we don't want to do because it'll mess up our understanding of what has happened on Mars currently and in the past. So we would like to keep it clean until, right, for some time into the future.
Mm-hmm. Yeah. I mean, this is always this balancing act, and probably this is one of those horses that is already out of the barn, which is that we can't get rid of the bacterial life on our spacecraft entirely. We can do our best job, but we can't get it all. And then if there are, and some of it is very hardy.
Yes.
Stuff that just needs just any edge in a way it can go to try and get moving. And so that's kind of interesting. So then, if, and I'm sort of imagining, there's people like if the inevitable thing that's going to happen is that there's going to be some kind of human research base on Mars. We're going to send astronauts to Mars. They're going to have some place, ideally in a place that's not anywhere near potential stores of underground water, but still this stuff's going to go airborne. Who knows what's going to happen?
Yeah.
Do you think that, like, how would this kind of change what kinds of plans NASA and ESA and so on might want to make for any future research station?
So it might change the plans in the sense that we have another tool to help us mitigate that contamination. So currently the thinking is because the UV radiation on Mars is so intense, that's going to do a big part of the job for us. Okay, so no doubt we are already and relying on that with our rovers and going to be relying on that UV radiation for human missions as well. But UV only gets so far, right? Is if it doesn't penetrate into the soil. And so anything that could have slipped between the cracks or get somehow protected, shielded from that UV was presenting a higher risk for that contamination. But if we know that the soil could potentially, the regolith could potentially also cause some harm to the organisms, that gives us another tool to just help know how much contamination we're potentially causing, and then how much is going away and how quickly.
Right. But it definitely sounds like this is the kind of experiment, like when a Mars sample return mission is completed, whether it's by the Americans or by the Chinese, this sounds like the exact kind of experiment that they should be running with the real stuff, because then we'll know.
Absolutely. Yes.
Yeah.
And I'm sure that is going to be in the works because we need all the information we can get before we send people to Mars because, yeah, it's not just us, right? It's us and our billions of microbial friends that go along for the ride.
Yeah, isn't that all we are? Is just a spacesuit for microbes?
Yeah.
Right. So what will happen next with your research, do you think?
So this was a first step in understanding how the tardigrades responded to the regolith. And next, we want to understand better how they would respond to other Martian conditions. And so a next step is looking at them in Martian atmospheric conditions, pressure conditions, and also with some ionizing radiation as well.
Yeah, and I know those labs exist. They have them in Europe and they have them in the US that you can expose it to. You can make it like it's Mars with the radiation, with the and I also know that they have experiments on the International Space Station where they will open up panels and leave various life forms, moss, bacteria, things like that, exposed for sometimes years at a time to the harsh vacuum of space, and incredibly, some Earth life can even go dormant and then come back after that, which is mind-blowing.
It is.
Yeah. Corien, what are you obsessed with right now?
I am obsessed with just microbiomes everywhere. I do appreciate that there's more awareness now of microbial communities and populations in just all sorts of strange places that help our world function, help us be healthy as well. And I'm just so interested in how they are able to do that.
Are you, like specifically things like our gut microbiome and things like that? Yeah. Okay.
Yeah. So our gut microbiomes, as well as our soil microbiomes, just everywhere. It's really very connected, many different species. I currently am helping a colleague look at the gut microbiome of dragonflies to better understand those. And yeah, they're
That's interesting.
everywhere. And in many ways, these microbiomes are doing kind of the same thing everywhere, but also specialized for that particular niche that they are in.
I always find this idea really fascinating that if I say dig up a few, 100 grams of soil from my property, put it under the microscope, I am likely discovering new life forms in there, new kinds of bacteria that have never been observed. No one's ever described them before. That world, because it's so small, is just, utterly unexplored.
Yes. I I couldn't agree more. I've also been very interested in the things we have not yet discovered, right? So a paper came out just in, I think, November last year about this new micro eukaryote that looks like a space station. And it is just crazy, but nobody had seen it before, really, and described it before. And it's just this amazingly ancient organism that lives its life I think it's from the marine sediments. And it's just a crazy thing. And there's so much crazy stuff out there still, right? We are just constantly finding organisms that change what we think about how cells should be.
Yeah, my wife is a macro insect photographer,
Really?
and before we had met, it had never even occurred to me that if you want to go see wildlife, you got to go go where the lions are, go where the bears are, and so on, right? And then we went for a walk with her camera, and we just like stopped at one shrub. And that was our whole day, was just all of the life that was going on. And that's stuff you can see, like, oh, there's this tiny little, it's little, I forget, they're like little hoppers and various leaf hoppers and just various kinds of bugs that are often like very small. And yet when you actually take a picture of them, suddenly you can see it's all of its sort of incredible complexity and fascinating behaviors and so on. And then, take it to the next level, start digging around in your soil, and you can just sort of see a whole other world as well. And I'm really fascinated by that. Like I said, I want to get a microscope. There's just this idea of how you can actually sort of test or see how good your soil is just by seeing the kind of activity that's going on in the soil. What are the good bugs? What are the ones that are, do you have the right combination of life in that biome, and what can you do to boost it? So yeah, it's very interesting to me too as well. Awesome. Well, thank you so much. Good luck with your research, and hopefully one day we'll get our hands on that actual Martian regolith to do the test again.
Yes, I hope so. Thank you.
All right, take care. I hope you enjoyed that conversation with Dr. Bakermans. Now, I have a longer conversation with her where we talk about her other research, which is into bacteria that can replicate at extremely low temperatures, like down as low as minus 20 degrees Celsius, which is kind of amazing that even at those cold temperatures, bacteria can keep doing what it does. And it sort of makes you wonder if that stuff in your freezer is still good. So as always, that longer conversation is available over on Patreon. Now, you don't have to pay. It's available free. You can be in an incognito browser, enjoy the interview, and watch it ad-free over on Patreon. I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Barely Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bela, Cooper and Ellie, Darkfinger, David Gilton, David Matz, Evan.pro, Greg Feely, James Clark, Janice Smith, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Simmons, Michael Purcell, Nordspace, OneStepForAnimals.org, Ren Kaidu, Richard Williams, Sean Sargent, Stephen Fallon-Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldemort Galactic Defender, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. People always ask me about the ethical concerns of exploring Mars, and this is one of the big ones, which is the forward contamination of Mars from Earth life. That if our hardy Earth life can actually gain a toehold on Mars, and as we start to explore larger and larger regions of the planet, what if we just keep finding tardigrades? What if we just keep finding cyanobacteria, Deinococcus radians, just the most hardy life forms that Earth has to offer? And that would suck because, if there was life on Mars and it was completely independent from Earth life, then this would be a whole different kind of abiogenesis. How did life form on Mars? Are we related? When do we share a common ancestor? I mean, we have so many questions about life, and that the implications of that will have implications for life in the universe itself. And so if we can step lightly on Mars and explore it and understand it in the most pristine way that we can, the better that is for us to be able to understand the universe and life and be prepared for what we might find out there in the cosmos. All right, we'll see you next time.